Okay, so let's talk about the step size that has been there since we started talking about the gradient descent algorithm. And so we said that we have to take these like small steps in order to reach at the bottom of this valley, right? And this is also shown here in sort of a 3D space, right? And like, what is the right size for the steps? Here are some examples. So let's say if eta is too large or the step size is like really, really large, you can see that the way this is going to work is if the step size is large, it's going to bounce a lot throughout this before reaching to the minimum. And what can happen, like the downside of this approach is that sometimes you take such big steps that Taylor approximation is not valid and E in becomes too large and it just like goes, as you can see here as well, it goes in all directions, right? So that's not really good for the running of the algorithm. The other is if eta is too small, then what happens? Like if we are, that's good in a certain way that like we will not violate any of the conditions here and we will eventually reach at the bottom. But then the downside here is that if we are too far away from the bottom, right, then it will take us forever to reach the minimum. This will take a lot of time again, including some, so that is going to include some inefficiencies in our algorithm. So what should we do? Well, one approach could be that we don't fix my eta. In fact, we make it a variable, and as you can see, it's eta t, which is like depending on the iteration. So the idea being that if we are far away from the minimum, then we should take bigger steps, large etas. And as soon as we start coming closer to E of in, or sorry, like the valley or the bottom, then we can take smaller steps. Okay, so how do we ensure that, right? Generally speaking, it's not easy to do that, but we can try. Now, from our knowledge of calculus, we know that if we are close to the minimum, then definitely the gradient of E of in must be really, really small or maybe even close to zero, right? And if we are far away from the minimum, then this must be like really, really big or greater than zero at least, right? So basically what's happening here is that the norm of the gradient, right, can help us decide the size of the step, correct? So basically what we're saying here is my step size needs to be proportional to the norm of the gradient of my E of n, right? And so this is an important observation. And so what we can do is if we go back to our update rule here in the gradient descent, and instead of eta, we come up with like an eta times the norm. What will happen is that this term will go away, right? Because this is proportional to this norm, right? And so our update rule becomes, like in our update rule, we'll have the norm cancel, which means we are saying move in the direction of the negative gradient, but with a step size that is proportional to the norm of the gradient. So this update rule, rather, I would say with like this new thing that came in, right? And we just have eta and maybe we can like replace it with eta t and just the gradient of E of n. Right, and then there are certain technicalities. So mathematically, I'm not sure if we have the negative sign or not, but we can check that. That's not important. The important thing is that we get rid of the denominator here, and this exact update rule, when applied to gradient descent, is like it gives it the name gradient descent. We don't have the normalized gradient descent anymore. Right, so this is the gradient descent algorithm actually. Okay, so all of that is great. Why is gradient descent so good? Because it works for any differentiable E in. So why is gradient descent good? It is good because it works on any E in of W that is differentiable. We just saw that. But there is a downside to gradient descent, and that is that it can be inefficient. Why is it inefficient at times? With larger data sets, especially, and with lots of features. Now think about the E in equation. Right? If we remember, there was that E in here, right? And so here I'm trying to, like with all the data, if you think about the larger picture of gradient descent, what I'm trying to do is in one iteration, I'm trying to compute the gradient of E in, right? And then also updating my weights, right? Updating weights. So these are the two things that I have to do. So updating weights is going to be an order d plus 1 operation, right? Why? Because d is the dimensions of my data. And if you think about the gradient, like in one iteration, I need to take care of the entire data set as such, right? So this is of the order nd, which is huge if you think about n and d. And so how to get rid of this like inefficiency? Basically, the question is how can we roll down? How to roll down efficiently? Right, that's the big question. Well, the answer to that question is that we have something that's known as stochastic gradient descent. The one that we have looked at just now, like the gradient descent here with the updated, like this update rule, is actually known as batch gradient descent. So if you come across that term, you know that this is batch gradient descent where we take everything together. But now with stochastic gradient descent, we have certain updates that we need to apply. Now, stochastic gradient descent does not guarantee minimum like gradient descent does. And so it's very similar to my PLA, the perceptron learning algorithm, in the sense that we do updates. So let me redefine my error term, like in a more generic way, sort of, is the sum of I is from 1 to n. And remember, this is a function. The pointwise errors, when we talked about them, we defined like in general, the error for this problem is a function of these. That's what we are saying here, right? And so the way stochastic gradient descent works is that pick a random point, right? Just pick any random point, let's say x of n, calculate this E, W, T, X of n, Y of n, we'll have Y of n obviously, and then minimize the like basically by calculating here, I mean minimize this. First calculate this and then minimize this for that one point only, right? And so if we minimize that, that is like make this data point better, right? That's what this means. So basically in terms of the update rule, what we're doing is this WT plus 1 is WT minus eta with the gradient of this error, whatever we have, like it's a function of x of n, y of n. Okay, so if you think about this one point, right, and randomly pick that point, so basically pick the point randomly, right, and then calculate the error, minimize the error, do the update using the gradient. So on average, the expected value of this gradient is still going to be equal to the gradient of my E of n. Why? Because we picked this point randomly, so it could have been any one of those in my data, right? And so using that logic that the expectation of this error is almost equal to En, right? Using that logic, what we can do is we can define this thing Wt x of n to be very close or almost equal to what we defined En earlier. So this is going to be log, sorry, this is L of n 1 plus E minus Yn W transpose Xn. Well, that's great. So again, we are having a very nice function because this is differentiable. And so we can definitely calculate the gradient of E with respect to W. And let it be a function of all of these. That's fine. You just differentiate this right here. It's going to be 1 over 1 plus E. This stays. And then this gets differentiated. So minus Yn Xn, sorry. Yn Xn, and then e to the minus Yn W transpose X of n. Okay, let me just like rearrange a few things. Minus Yn Xn, and remember this and this together, just like to remove the negative, and what you'll get is 1 minus e to the Yn W transpose Xn. Okay, so this here is like if you remember the overall gradient descent update rule was to have like the gradient of this thing in my equation in my update rule. So my update rule, or in my logistic regression now with stochastic gradient descent, is going to look something like this. And of course the step size stays, and 1 plus e to the Yn transpose X of n. Okay, so that's it. That's the update rule. That's the only thing that gets added in my stochastic gradient descent. And again, it kind of relies on the fact that on average, the minimization will proceed in the right direction, But of course, because we are picking one point at a time, or maybe like practically speaking, sometimes we pick few points at a time. And so the movement is going to be a little wiggly, but in the long run, these random fluctuations will cancel out. And think about the computational cost. It's cheaper by a factor of n, which is huge, right? Because we're computing the gradient for 1 point per iteration rather than for all at n points as we did in gradient descent. Okay, so here is a picture of how both of them compare, like the gradient descent versus the stochastic gradient descent. Now notice that for stochastic gradient descent, it's similar to PLA in that it decreases the error with respect to one data point at a time, right? So minimizing the error on one data point may interfere with the error or the rest of the data points that are not considered, right? So it might mess up the rest of it. But similar to PLA, the interference cancels out on average, as we just said, right? In practice, stochastic gradient descent is successful and it beats the batch version like most of the times. It beats just like this is the batch version, right? So it beats that most of the time. And in fact, this stochastic gradient descent was an important algorithm when, remember, we talked about the $1 million Netflix competition. So it was used there. It scales well to large data sets. And so it's like really suited to those kind of problems. Well, that's it in lecture 9, and then see you in lecture 10.